Hello everyone, welcome to the lecture again. Today we are going to discuss the principle of virtual work. Principle of virtual work is required to study the equilibrium of a particle or of a rigid body or the connecting rigid bodies. Now to develop the principle of virtual work, we need some basic concept like what is the constraint motion, what is degree of freedom, generalized coordinate, virtual work, virtual displacement and so on. So, let us first discuss what is a constraint motion. So, suppose I have an object and this object is restricted to move in certain direction. So, these are the example of the constraint motion. So, by definition this is the motion of an object in a restricted way. We will look at this example, but as of now take this definition. Now, another concept that is required is the degree of freedom. So, generally this degree of freedom is denoted by f, and it is the least possible number of coordinate to describe the system completely. So, for example, you have a particle and let us say that particle is moving in one dimension. In that case, the degree of freedom of the particle is 1. We will again look at the examples of various degrees of freedom. Now, let us look at generalized coordinate. So, any f coordinate let us say q1, q2, q3 dot 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 qf, which completely define the position of a system, okay, and here note that f is the degree of freedom or called generalized coordinate of the system. Now, with this definition, let us look at the example. So, let us say I have a simple pendulum and let us say this pendulum is suspended from point O and the length of the string is L. So, this length will also be L and let us say the mass of the particle that is attached to it is m. In that case, so this is just the example of the motion of a simple pendulum which is confined to move in the vertical plane. So, here you can see that just by one coordinate which is theta, I can define where the particle is because L is fixed. So, therefore, its degree of freedom or DOF, which we also denote by f, is equal to 1. Again, why? Because just by one coordinate theta, I can define the position of the particle. And the generalized coordinate is theta. Note that it is not x and y because then you require two coordinate system x and y, but here I am saying just by one theta you can define the position of the particle. So, again it is the least possible number of coordinates. So, theta is 1. So, this is the least number of possible coordinate. So, therefore, degree of freedom is 1 and the generalized coordinate is theta. Now, let us say I have a particle which is free to move in 3 dimension. So, let us say this is x axis, y axis and z axis, and I have a particle here. So, for one particle, the degree of freedom will be 3 and the generalized coordinate can be x, y or z, or in cylindrical coordinate they can be r phi z, or in spherical coordinate they can be r theta phi. But the degree of freedom will be 3 because it can move in 3 dimension. Similarly, if there are n particles, in that case the degree of freedom will be 3 times n. Now, if the system of n particles has k independent constraints, then the degree of freedom will be 3n minus k, because in k ways it is restricted. So, for example, let us look at the motion of a particle which is restricted on the surface of a sphere. Okay. So, for example, let us say this is the sphere and a particle can only move on the surface of the sphere. So, in this case its distance from the center of the sphere r, this has to be fixed. So, this is one constraint, and for a particle which is free to move, degree of freedom is 3 and there is one constraint. Therefore, in this case the degree of freedom will be 3 minus 1 equal to 2. And what are the generalized coordinate? Well, we can take, because of the spherical symmetry, we can take r, theta and phi, but since r is fixed, so therefore theta and phi will be the generalized coordinates. Now, let us look at the example of two particles that are constrained to maintain a constant distance from each other. Okay. So, for example, this is one particle, this is another particle, and in between the distance is fixed. So, in this case the degree of freedom f will be 3 into 2 for two particle minus one constraint. So, it will be 5. Now, let us look at a rigid body. Now, for the rigid body, a rigid body can move in the x, y and z direction, and it can also rotate along x, y and z direction. Therefore, total number of degree of freedom will be 6. So, there are 3 translation plus 3 rotation. Okay. You can also think of it like following. So, let us say in the rigid body you have n particle. So, let us consider the first particle. So, for the first particle which is independent to move, we have 3 degree of freedom. Now, for the second particle, so let us take another particle. For this also we have 3 degree of freedom, but then it has to maintain a constant distance between them. So, therefore, for this the degree of freedom will be 3 minus 1 equal to 2. Now, let us look at the third particle. In this case the degree of freedom will be 3 minus, so it has to maintain a constant distance from this and a constant distance from this also. So, 3 minus 2 equal to 1. Now, you take the fourth particle. Okay. So, in this case we have 3 coordinates, and then it has to maintain a constant distance from all 3 particles. So, therefore, it will be 0 and subsequently for all the particles it will be 0. So, total number of degree of freedom for the rigid body will be 3 plus 2 plus 1 equal to 6 again. Now, let us look at another example, which is, let us say, double pendulum. Okay. So, let us say this double pendulum So, one arm of this has a length L1 and mass, let us say M1 is attached to it, and then you have another arm of length L2 and mass M2 is attached to it. Now, to define this system or the position of mass M1 and M2, I need theta 1 and I need theta 2. Therefore, its degree of freedom will be 2 and the generalized coordinate will be theta 1 and theta 2. So, my q1 and q2, which are generalized coordinate, in this case will be theta 1 and theta 2. Now, let us look at the displacement of the rigid body. So, suppose I have a rigid body and how can I displace it? Okay. So, one way to displace a rigid body, let us say from one position to any other position is by pure translation. So, what do I mean by that? Suppose I have a rigid body and you want to displace it. So, we can just do pure translation, rotation is not involved. The other way of displacement is by pure rotation. So, again you have a rigid body and let us say you fix some axis on it and then you rotate the rigid body about that fixed axis. But in general, the general displacement is both translation and rotation. So, this is translation plus rotation. Now, let us look at the work done by a force. So, all these concepts are required to us. So, let us look at the work done by a force. So, we know that the work done by a force during displacement is du equal to F dot dr. Okay. And if you want to calculate the total work, so you integrate this F dot dr and you will get the total work. Now, we also know from the high school that W is equal to F dot d. This can be written as F d cos theta, and now if your theta is, let us say, 90 degree. So, that means you are applying a force which is perpendicular to the direction of the motion. In that case, the work done will be 0. If your theta is between 0 to pi by 2, in that case work done is positive, and if your theta is large than pi by 2 and let us say less than pi, in that case your work done will be negative. Now, let us look at the work done by a couple. So, let us say I have a rigid body, and on this rigid body a couple is acting. So, let us say F and minus F, and let us say there is one more force. Okay. So, let us call it F prime, and because of this, let us say you have the translation. So, we are discussing the translation. So, now let us look at the total work done by these forces. So, total work done will be F into D plus F prime into D minus F into D, and this comes out to be F prime into D. So, you can see that no work is done by a couple during translation, because the effect of F d and minus F d got cancelled. Now, let us look at the work done by the couple during rotation. So, we have a rigid body, and on this rigid body, let us say a couple is acting. So, you have minus F and you have plus F, and let us say the distance between them is A, and because of this the body is going to rotate. So, let us fix our axis at minus F, and this body rotates. Okay. So, let us say it rotates by a angle d theta. So, therefore, this will be dr, and in this case the work done by the force will be F dot dr, okay, because you have this force and the body is displaced by dr. This force is not going to work because I have passed the axis through this. So, therefore, for this point dr will be 0. So, it will be F dot dr, and this will be F dot dr is related by A with A d theta. Okay. Now, you also know that force into the distance between them. So, one of the force and the distance between them is the moment. So, therefore, this becomes m d theta. Therefore, during rotation the work done by the couple will be du equal to m d theta. Okay. Now, if you have finite rotation, so total work done during finite rotation will be u equal to integral m d theta. Now, with this general definition, now let us look at what is virtual displacement. So, first of all, we know that if a number of forces act on a body, but the forces are in equilibrium, then the forces do not displace the body from its natural position, and no work is done by these forces. So, this is the definition of the equilibrium. Now, what is virtual displacement? Any assumed and arbitrary small displacement, let us say away from the natural position and it should be consistent with the system constraint is called a virtual displacement. The important point is the displacement that you are assuming, it should be consistent with the constraint that is imposed on the system. Let us look at the example. So, first of all, let me tell you that this virtual displacement it can be just displacement, let us say dr, or it can be rotation d theta of the body. Okay. Now, let us look at the virtual displacement by example. So, let us look at example of a body that is kept on the surface, and let us say you apply the force like this. So, you have to note that what are the constraint? The constraint is that this body has to be on the surface. Okay. But suppose you say, well, that a small displacement I am going to assume like this. Under the action of this force, I am going to assume that this is the displacement. Note that this is not virtual displacement, and the reason is it is not consistent with the constraint that we imposed. Okay. So, this is not consistent with the system constraints. So, therefore, this is not the virtual displacement. Now, let us look at the second example. Let us say you have the following assembly. So, you have a pin joint, so let us say I have two bars which are hinged at this point, and it is supported by a pin joint and a roller support. Okay. So, this roller can move only in the horizontal direction. This point is fixed and the length of the bar will also be fixed. So, therefore, this is the example of a constraint motion. Let me ask, what is the degree of freedom? Well, by single coordinate theta, I can define the position of this roller. So, therefore, the degree of freedom is 1, and the generalized coordinate is theta, because with this theta I can define the position of this roller. So, the generalized coordinate is theta. Now, what is the virtual displacement? Again, we have to respect the constraint that is applied on the system. So, when you apply this force, under the action of this force, you can assume that this body or this connecting body, it moves like this. So, note that this point is fixed, the roller is moving in the horizontal direction, and the length of the bar is also fixed. So, therefore, this qualify to be called the virtual displacement. So, we have virtual displacement, and virtual displacement is d theta. Okay. So, note that you can also claim that I can write down this in terms of x and y coordinate, and therefore, the virtual displacement will be dx and dy. But since our generalized coordinate is theta, therefore, you have to convert this x and y in terms of theta. So, the point is that this delta x and delta y, if you write down in that form, then it will be a function of delta theta. Now, let us look at another example. So, this is the example of a folding linkage. So, the concept is following: you have a roller and you have a hinge pin, and with this a folding linkage is connected. Okay. So, let us say you have a force in that direction and you apply a force in this direction. Now, this is nothing but a folding linkage. So, again with a single coordinate theta, I can define where this link is. So, therefore, its degree of freedom is 1, generalized coordinate is theta. Now, let us look at the virtual displacement. Well, under the action of this force P, I can assume that this link is going to be like that. So, let us say this angle is delta theta. So, note that I have respected whatever constraint were applied. Okay. So, therefore, the virtual displacement is delta theta, and again if you want to write down this in terms of x and y, then you have to note that since my generalized coordinate are theta, therefore, this x and y I have to write down in terms of theta. Now, let us look at another example. So, this is a let us say a double pendulum. So, you have this length as A and you have weight W1, then you have this length as B and weight is W2, and to keep this in equilibrium you apply a force P. Okay. So, let us say this angle is theta, this angle is phi. So, therefore, the degree of freedom for this system will be 2, the generalized coordinate will be theta and phi, and the virtual displacement will be delta theta and delta phi. So, under the action of this force you can assume that this assembly is going to move like that, and this angle is delta theta and this angle is delta phi. Now, with the concept of virtual displacement, now let us discuss what is virtual work. So, the definition is the work done by any force F during the virtual displacement, let us say delta r, is called virtual work. Okay. So, for example, if you have translation, then delta u will be F dot dr. Similarly, if you have, so let me write down, similarly virtual work done by a couple M during a virtual angular displacement delta theta will be delta u equal to m delta theta. After understanding the concept of virtual displacement and virtual work, now let us look at the principle of virtual work. So, the statement is following: if a rigid body is in equilibrium, then the total virtual work of the external forces. So, we know what is the external forces now. They are acting on the rigid body is 0 for any virtual displacement of the body. Okay. In equation form, if you calculate delta u, which is the virtual work, it should be 0. So, note that here delta u is total virtual work, and you have to calculate for the external forces, for example, the forces that you are applying or the mass of the object and so on. Now, if the virtual displacement is consistent with the constraint, then all reaction and internal forces are eliminated. That means you do not need to consider them, and the reason is because the total work of the internal forces at the various connections or reaction points is 0, and only the work of the forces external to the system, for example, load, applied forces and friction forces, etc., they need to be considered. So, this is the same point that I mentioned here, that you need to consider only the external forces. In the next class, we will look at the virtual displacement, virtual work and the principle of virtual work by various examples. With this, let me stop here. Thank you.